Hello, this is FlippedHarber for Precalculus. In this video we'll be talking about section 4.4, Properties of Logarithms, Curve Fitting. Our objectives for this lesson are to write a logarithmic expression as a sum or difference of logarithms, write a logarithmic expression as a single logarithm, evaluate logarithms whose base is neither 10 nor e, and draw scatter diagrams of exponential and logarithmic data. The outline for this video, we'll talk about some properties of logarithms. We'll be writing expressions as a single logarithm. We'll be taking a look at several theorems dealing with logarithms, and we'll end by looking at some examples. So first of all, before we talk about our properties of logarithms, I want you to remember that when I look at a logarithm, when I see the log base a of m, what this is really saying to me, and it makes a whole lot of sense when we start talking about these properties, is this is asking me what power is going to go on A in order to create M. So this is all about figuring out what power is going to go on that base A. Okay, so let's take a look at some really basic properties of logarithms. Now, whenever we see log base a, that's basically saying that this logarithmic property is true no matter what the base is. It could be a base 2, it could be a base 10, it could be a base e, which is a natural logarithm. It absolutely doesn't matter. So the log base a of 1 is equal to 0 because, again, log base a of 1 is asking what power do we put on a in order to get 1? Well, we know that anything to the 0 power equals 1. Now the log base a of a should equal 1 because what power should I put on a to get a? Well, I need to put a power of 1 on it. So basically you can think of that as almost kind of canceling out. The log base a of a is just equal to 1. Okay, now we're going to talk a little bit deeper about some of these things. When we put a logarithm as a power, we have the potential that they will cancel. So the way that they cancel is if the base number that the exponent is on and the base of the logarithm match. They cancel each other out totally, and we're left with whatever letter or variable or number that the logarithm is acting on. You could think of the a and the log base a as canceling. Now the log base a of a to the r, we saw that the log base a of a is 1. Well, that is kind of a special case of this. The log base a of a to a power, well, they cancel and we're left with the power, and that's really why logarithms were invented, was to solve for a power, to remove that base number and give us a way to tease out that power. So these are basically getting to the uses of logarithms. We're going to actually end up solving equations with logarithms and exponents in the next section, and these are going to be very, very useful. But moving on, the log base a of m times n. So this is what we refer to as a product rule because m and n are being multiplied together. When we have the log of two or more things multiplied together, we can separate them out into multiple individual logarithms that are added up. So the log base a of m times n is equal to the log base a of m plus the log base a of n. Now, kind of the opposite is true also. If instead of multiplying m and n, if they are divided, we take the log of m minus the log of n. Another way to remember that, or to think about that, is that it's always the log of the top minus the log of the bottom. Whatever's on top minus the stuff that's on bottom. Now, if we have a power, regardless of whether things match, that power can come down in front. It is referred to as a factor rule because that r turns from being a power on m into a factor in front of the logarithm. Now the next one, the log base a of 1 over n, could be thought of as a special case for this because remember, 1 over n is the same as n to the first power. So that negative power can come out in front. Okay, so Here we see basically an example, but what we want to do is kind of put some of these rules, some of these properties that we just saw together and write this as a single logarithm. So we're starting out with an expression, things multiplied, things added or subtracted. We want to write it as a single logarithm. So it's going to be log base A of just one thing. So we have to figure that out. So we're going to apply these properties that we just looked at. And the first thing I'm going to use is that fact that the 2/3, that factor in front of the logarithm, I'm going to make it a power. So that's a 2/3 power on 8. Now you also see that I've gone ahead and figured out that 3 to the 4th power is 81. You know, if you don't know that, you just plug it into your calculator. 3 to the 4th power, you get 81. Now I'm going to go ahead and simplify those powers. So 8 to the 2/3. That means that you're going to square the 8 and take the cubed root. A fractional power is equivalent to a root. Or you could take the cubed root and then square it. The order really doesn't matter. And then go ahead, 81 minus 8 is 73. So now we're down to a log minus a log. And you need to get that work done so that it's just a plain old log plus or minus a plain old log. Now this next step, we're going to use another property, but you need to really look and make sure that your bases on your logs match. If these were not both log base A, I couldn't go any further. So since they're both log base A, I can go ahead and apply that property where a log minus a log is actually the log of the two things divided. So now it's written as a single logarithm. You're going to have several problems like this on your homework. A good example here of all of those properties working together. Alright, so let's talk about some theorems. Here's a really basic one. It does have its uses. If m and n are equal, then if we take the log of m, that's going to be equal to the log of n. Now again, you got to have the same log base. So that's log base A of m equals log base A of n. And the opposite is true. If we have two logarithms that are equal, if those logarithms are the same base, we can just deduce that the m and n are equal. So we don't really have to do any fancy math to get rid of the logarithms. We just say, well, if the logs are equal, then what the logs are operating on have to be equal. Again, that's only if we have the exact same base. If that was log base 3 of m equals the log base 2 of n, I cannot say that m and n are equal. Alright, here we see what's referred to as the change of base formula. Now this is actually a very, very useful formula, and what it lets us do is change a log base A into any log base that we want, as long as we follow those rules. You know, we can't take the log base of a negative number, we can't take the log base of 1. So as long as A won't be a negative, it won't be a 1, because they'll give that to you. You can't make B a negative. You can't make B equals 1. So we use this log base change formula a lot, because when we have an odd logarithm, we want to turn it into something that we can work with easier. So what we'll actually use more often is we'll change it to a log base 10. And that's the on top. When you don't see a base on a logarithm, it's implied that it's log base 10. Or we'll use this change of base formula to turn it into a natural logarithm. Now the reason that you'll be using these the most is because this is what your calculator can do very, very easily. It's got it programmed in. So if you're given a log base 3 of some number, you can turn it very easily into a log base 10 or a natural log that your calculator can do. Now let's take a look at some examples. Now this is a little bit weird. I really like problems like this because it really tests your understanding of what's going on here. Suppose that the natural log of 2 equals A. So the natural log of 2 is not a nice number. It's not a rational number. It's a repeating decimal. We're just saying that it equals A. And the natural log of 3 equals B. We want to rewrite these two logarithms in terms of A and B. So really my first step is to tease out where's my 2 and where's my 3 hiding at. So if you stop and think, 1.5, how could I rewrite 1.5 using 3's and or 2's? Well, pretty easy. 1.5 is 3 halves. So now I start to see that 3 and that 2, but I need to make it a natural log of 3 and a natural log of 2. Well, I'm going to use that property of logarithms that says, well, make it the natural log of the top minus the natural log of the bottom. Natural log of 3 minus the natural log of 2 is equal to b minus a. So we're going to apply a very, very similar concept here with the natural log of 0.5. I just won't have to use the 3. 0.5 is 1/2, so we see that 2 show up. And that 1 really isn't a big deal as far as logarithms are concerned. Logarithms with 1s usually aren't a problem. They work out very nicely. So what I can actually use is that logarithm of 1 over n, if you remember from earlier in the video. I'll just slap a negative out front and it's not a fraction anymore. So now negative the natural log of 2 means that it's equal to negative a. Okay, so here's another example. It's going to be like what you see in your homework. Express the logarithm as a sum or difference and express powers as factors. So again, we are wanting to separate things out so that it's natural logs added and subtracted, and instead of having powers on items inside the logarithm, we want to pull them out front. So here's what we want to work on. We've got the natural log of x to the 4th times the square root of x squared plus 1. So the first thing I see is that I have x to the 4th times the square root. So I'm going to separate that out into two logarithms. Logarithm of x to the 4th plus the log of square root of x squared plus 1. I guess I should be saying the natural logarithm. You don't want to change your base or anything if you don't have to. Now I've got to deal with the powers. So obviously I'm going to pull that 4 down front, but you're probably going to be a little bit surprised at the other factor that you see. We see that 4 come out front, but that square root, we can think of that as a 1/2 power. So that 1/2 can come out in front as well. Now I'm actually done with this one because that plus 1 really puts the brakes on doing anything else. I can't pull that square as a factor out because it's only acting on the x squared. It's not acting on the plus 1. So we're done here. We can't do any more. This is our final answer. Alright, so now we're going to do the exact opposite. We want to write the expression as a single logarithm. So we're going to want to take factors and make them powers, which we don't actually have any factors in this one. This is actually going to be a pretty easy example. We've got the log base 2 of something plus the log base 2 of something. And don't really worry too much right now about what the logarithms we're working on. You just need to apply the rule that when you have a log base 2 plus a log base 2, you can rewrite it as a single logarithm where you multiply the two items. Now obviously I can do some simplifying on this. I can make it 1 over x cubed, and I'm going to go ahead and, I mean, this seems a little weird, but it kind of depends on where you want to go with this, but I'm going to go ahead and make it not a fraction by putting a negative in front of that log base 2. I'm going to leave the 3 there. I'm going to leave the 3 as a power rather than bring it out as a factor. The only reason I did this is so that it doesn't have a fraction. So that one's all done. Now let's try to find the exact value of the expression. Now whenever you see find the exact value, they're pretty much saying don't touch your calculator. You've got to do this without using your calculator. Okay, and that means that you're going to have to think about these properties. You're going to have to do a little bit of work and figure it out. This will work out nicely though. So I've got 5 to this rather lengthy power. All that other stuff is a power on 5. So I've got the log base 5 of 6 plus the log base 5 of 7. Now the 5 and the log base 5 will cancel, but not until I write it as a single logarithm. So instead of 2 logarithms, I need to get 1 logarithm. And the way I do that is I multiply the 6 and the 7. So I have 5 raised to the power of log base 5 of 42. Now that it's a single logarithm, the base matches the base number. They cancel out, and it's just a plain old 42. Alright, moving on. Here we're going to kind of get a flavor of what's going to happen in our next section. They want us to express y as a function of x. The constant c is a positive number. Now they make that statement because we're not going to run into any problems trying to take a logarithm of c if we want to. Remember, you can't take the logarithm of a negative number. You can't use a negative number as a base on a logarithm. So we won't run into that with this problem. So we have the natural log of y equals the natural log of x plus the natural log of c. Now you might just want to say, well, I'll just get rid of all the natural logs. Well, that's what we're going to do, but first we need to get rid of that plus. We need to get it to be a natural log equals just a single natural log. We're not factoring out the natural log. It's not like, there's a 4 in the front of the y, the x, and the c. This is an operation, and there's steps that we have to follow. So my first step is to combine the two natural logs on the right side. And obviously I do that by multiplying the c and the x. Now I can just throw those natural logs away. Natural log of y equals the natural log of cx. Well, the only way that's possible is if y equals cx. So we're starting to get a taste for what's going to happen in the next section, where we're actually going to be solving for equations with natural logs and exponentials in them. Let's do this again. That was so much fun. Let's do another one. Express y as a function of x. The constant c is a positive number. So here's my equation, and one of our terms doesn't have a natural log. So how are we going to deal with this? Well, the way we deal with this is we get the two terms that have the natural logs together on one side. Just do that by simple addition or subtraction. So I subtract over that natural log of c. I'm going to, again, combine those two natural logs. I have to get those two natural logs down into one. So, that's supposed to say a natural log of y over c. I guess that's what happens when you cut and copy stuff. But that's supposed to be a fraction instead of a product. But we're going to press on instead of restarting this video. So now we put it as a power on e. The e in the natural log will cancel out. And again, that's supposed to be y over c, not cy. But on the other side of the equation, we have e to the 5x. That doesn't cancel, nothing matches to cancel, so we just leave it the way it is. And you're actually supposed to multiply over the c. Alright, so obviously I'm going to have to fix this video in the future, but deal with it for now. Let's take a look at our last example. This is going to prove useful for some story problems. They're going to give you an equation like y equals 999 times 0.898x. Now, it's better for us when we want to punch it into a calculator. We're actually going to be fitting it to a curve. It's better for us if instead of this weird base number 0.898, if it was a power on e. So we need to fit it into this new form. A equals a naught e to the kt. Now, part of this is really super easy. You could probably figure out that a naught is going to equal my 989. My x, my variable in the top one, is going to be t, my variable in the bottom one. That's not really the big deal here. The big deal is that 0.898 is my e to the k. So that's what I have to actually figure out. I set e to the k equal to the 0.898. Now, solving this is not a big deal. We take a natural log of both sides. K equals the natural log of 0.898. Go ahead, punch that into your calculator. That means that K is equal to negative 0.1076. So that means that y equals 999 times 0.898 to the x can be rewritten in the form a equals 999 e to the negative 0.1076 t. Really, all you've got to do is deal with that 0.898. That's really all the work is. Alright, so we're all done. Time for you to try some of these on your own. I will see you in class, and I will see you online.